junk to the 1 minus 3 is? Good, so negative 2/3, and then the derivative of the inside is? 2x. All right, so that's u prime, and then v prime is negative 2x, and then you just plug it into the quotient formula. Was it this part that was giving you trouble? Yeah, just finding an exponent to give it. So the lesson here, guys, is if you have a function under a radical like this, go ahead and wrap the entire thing if it doesn't already have an exponent. Give it an exponent. So if it's not wrapped with like a square or a cube or a 1/3 or 1/10, whatever it happens to be, give it an exponent of 1 so that you can give it a full exponent when you go to take the derivative. Does that make sense? Okay. That was that one. Number 5 on 9.9. Is that the demand for a local cable TV service? Okay. Where P is the monthly price in dollars and X is the number of subscribers in hundreds. So, I don't know where that came from. So demand is P, which is also price. Okay? In dollars. And X is subscribers. In hundreds. Okay. We have a function P equals 80 minus 0.4x. Okay, find the total revenue as a function of the number of subscribers. So that's part A. Well, what did I tell you guys about the relationship between price and revenue? Did you read your handout? Yes, revenue is price times quantity. So what do you think our revenue is gonna be here? Nemo knows more than he thinks he knows. It's a good thing. Don't overthink it, guys. If you have P, how do you make this into a revenue function? You do what to it?
You just multiply by x.
Yeah, you multiply by X, exactly. So my revenue is gonna be price times quantity, which is 80x minus 0.4x squared. That's it. That's your revenue. Okay. Part B, find the number of subscribers when the company charges $50 per month for cable service. So we're looking for a number of subscribers when the price is 50, right? So what do? I'm looking for X, number of subscribers, when P is $50. Plug in 50 for P and solve for X, right? So I can either do that here, no, I can't do that here, but I can do it here, right? So part B, I'm like a mess today. This is part A. Part B was when the price is $50, find the number of subscribers. So I just set in price is 50, and I'm gonna solve for X. Right, not so bad. So let's see. 0.4x equals 30. I'm just gonna move the 50 over here and the 0.4 over here. That should be nice. If I divide both sides by 0.4, I get x equals basically 300 over 4, which is 75, or, because it's in hundreds, 7,500 subscribers.
Can I ask a question?
Yes.
Wasn't the price function giving, or the P equals 120 minus 0.4x in the
120.
Yeah.
Do you have a different set of numbers in yours?
That's
maybe?
what mine says too.
Okay.
P equals 120 minus 0.4.
Same.
Okay.
So just substitute your numbers. they're working out of a different edition, or I'm working out of a different edition, but no biggie. Okay, all right, so, is this the one you guys got stuck on? Who's asking for this one? Where'd you get stuck? Ah! Does it make sense? Okay, so then, part C, how could the company attract more subscribers? Don't think about this in math terms, think about this in your own experience. What would make you want something more? Yeah,
If you lower the price.
damn straight, so just lower the price, they'll attract more subscribers. And then part D, find and interpret the marginal revenue when the price is $50 per month. So we would take the derivative and shove in P equals 50. Ooh, but hang on, when P equals 50, what does X equal? 75. So we're not actually shoving in $50 per month into the revenue function, because revenue is in terms of number of subscribers, right? So first we find the number of subscribers at $50 per month, so that gives us an X of 75. So this is what we would be plugging into our revenue function. Does that make sense, you guys? Okay. It's super important to label every single one of these things. Notice that I always have a left-hand side to my equation. How many of you guys have just gotten to the point where you just write down the function and then do things to it? How many of you? Yeah, get out of that habit, because you're gonna start working with multiple functions. You're gonna wanna know which one's which from here on out. So label each one. It's gonna make your life a lot easier. Ruby? Questions? Okay. Number 7. Graph the marginal revenue function from problem 3. Problem 3 was some revenue problem. Okay, so my revenue from problem 3 is this the problem you guys wanted? This is minus 0.01. 36x minus 0.01x squared. And then it says graph the marginal revenue. So what's marginal revenue here? Yeah, 36 minus 0.02x. Okay, that's linear. It's gonna look like this. So at some point, this is gonna cross the x-axis, right? And when it crosses the x-axis, wherever that happens to be, here's my x-axis, and here's my marginal revenue. So wherever this crosses the x-axis, that's maximum revenue, isn't it? Or that's the point at which maximum revenue is achieved. Because when you're graphing a derivative, remember, you're not graphing x versus y, you're graphing x versus slope. So the slope is positive in this region up to this x. The slope is 0 at this x, and the slope is negative everywhere after. So your original function will cap out at that point and then start to decrease. So this would be your original revenue function. Positive slope, 0 slope, negative slope. Positive slope getting close to 0, 0 slope, negative slope going away from 0 and getting steeper in magnitude. Okay. What is the next part of that? At what value of x will total revenue be maximized for problem 3? Okay, part C, what's the maximum revenue? So again, whatever you find this x value to be, that's the production level that maximizes your revenue. The way to do that is the way to find the corresponding maximum revenue. Right over here, this is maximum revenue, is to take that x value and plug it into the revenue function to get the corresponding maximum revenue. So think about it this way, it wants a revenue, where are you gonna plug x? Into a revenue function, right?
So, think about it in terms of X is production, and maximum revenue is just a special kind of revenue, right? So we can plug any X in and get the corresponding revenue out. If we know this X, we can shove that X in to get the actual maximum revenue. Does that help? Awesome. What else, guys? This actually feeds directly into what we're about to do, so that was a great question. So today we're moving on to the stuff that will be on test 2. You guys kind of have a funky schedule because I'm trying to stall for today may actually be the day that you get to leave early, which is good. Unless, Emily's excited. Why are you so excited?
So we could stay and do homework.
Yeah, you paid for the time, so I have a class in here after you guys, so I'm just gonna sit here and do whatever. So if we happen to finish early, which is likely, I'm just gonna park, and you guys can work and ask me questions and do whatever. We can turn it into a lab, okay? It's a homework lab. So, put that away. Chapter 10.
So annoying.
10.1, I call it sketchy curves. Because today we're gonna be working on graphing curves and understanding the nature of those curves. Okay? But before we touch on that, I need you guys to be able to take a second derivative. The second derivative, which is f double prime of x. Whoa. So, what have we learned about functions so far? If we plug an x into a function, what do we get out? Yeah, we get out a y. If we plug an x into a derivative, what do we get out? A slope. Well, there's another one. If we plug an x into a second derivative, we get out what's called concavity. Concavity is a really easy concept. If the function looks like this, is that a happy or a sad face? That's a sad face. That's concave down. We don't do concave and convex anymore because no one could remember the difference. So we just say concave down. And is that a happy or a sad face? Here. Seriously, don't overthink it, guys. It's a happy face. This is concave up. Okay. So when we're doing second derivatives, we're looking at concavity. And I'm going to be touching on this multiple times over the next few days. So let's look at a function. Okay. So let's say I have some function that looks like this. That's better. Okay. Some function. The first derivative tells us where the slopes are 0. So you guys are going to tell me where that is. Here. So the first derivative equals 0, and here. The first derivative equals 0. Now, with the second derivative, we're looking for the places where the concavity is 0. And anytime you switch from concave down to concave up, or concave up to concave down, you have to cross the axis, right? So for graphing x versus concavity on the second derivative, remember, just like x versus slope, where the derivative crosses the x-axis, that's where the slope is 0. Where the second derivative crosses the x-axis, that's where your concavity is 0. So tell me approximately where concave down, which is this region, right, goes to concave up down here. Just just approximately where? Somewhere in here, right? Gesundheit. So this is where the second derivative would equal 0. So I want you guys to kind of look at this function, and I want you to use slope and concavity to redraw it. Let me show you what I mean. So let's start with slope. The slope is 0 here at this x, so I have a 0 slope here. What kind of slope do I have in this region on the original function? Yeah, it's positive, it's growing, right? So I'm just gonna label that positive slope. What kind of slope do I have in this region?
Could you go back and one of the question and
Missed what?
when you talked about after the lines, and you did the plus and minus and the 0?
Oh, okay, so I'm just relating the places where the slope is 0. I'm just trying to give a slope profile to this function. So I found the places where the slope is 0. I'll get to this one in a second. And then I'm just analyzing the slope visually here. So this is a positive slope in this region, but in this x region. Okay, so what about this x region? What kind of slope do we have? It's negative. Up to this point, and then we get another 0 slope. And then after this, what kind of slope do we have? Positive. Okay. All right, that's not so bad. Now I'm going to mark this concavity. So this x, whatever this was, has a 0 concavity, right? Because that's where it's changing from up to down or down to up. What kind of concavity do we have in this region to the left of that spot?
Down.
Yeah, it's concave down. And I just draw it with a giant down shape and a negative sign to differentiate between what I'm marking as slope and what I'm marking as concavity. What about here after this point? It's concave up, isn't it? Okay. So now I'm going to redraw that function using just that profile. So what did I have? Here's my slope. So I'm going to redraw my profile. There's 0. Here's positive. Here's negative to like here, right? Let's see. Let's be consistent, shall we? 0 slope here, and then positive slope after that. And then on my concavity, give it a little more room. On concavity, I had a place where it was concave 0 right about there, and then I had concave down, and then concave up for this region. You guys ready for me to draw your original function just using this cube? We're going to start with the first distinct region up to this point. What kind of slope did it have? What kind of concavity did it have? Negative. So I'm going to draw something that has a positive slope and a negative concavity up to that point. You guys cool with that? Okay. Now, second distinct region has what kind of slope and what kind of concavity?
Negative.
Negative, negative.
It's going to-
So it's just going to look a lot like that, right? Okay. All right. Now, this is where it changes concavity. So I'm going to go to happy face now. What's my next region? Negative slope, positive concavity. Okay. Next spot is a 0 slope, so I'm bottoming out. And then the last region is positive slope, positive concavity. That looks real similar, doesn't it? I didn't look at it once. So we can use the first and second derivatives to define regions of importance in a function. Maxima and minima at times are just as important as this spot right here where the second derivative equals 0. The one major application, write this down, kiddos, chickens. The one major application we use the second derivative for is something called the point of diminishing returns. So this second derivative equaling 0 is the point of diminishing returns. You guys know what that means? Anybody have a guess?
So at that point, you don't get any value.
Yeah, after that point, you don't get any value. Look at what's happening here on this particular function, guys. Whatever it is that you're looking at is increasing, and the rate of it is increasing, as in it's growing, it's also getting steeper. So it's growing faster as it goes on until this point. It continues to grow after that point, but what's the slope doing?
Staying constant.
Yeah, it's going back down to 0. The slope doesn't stay constant. The slope is changing as we go. It's still positive, but it's going back down to 0. So we're not getting as much bang for our buck. We're not growing as quickly as we used to be. Why do we care about this? How many of you want to make 6 figures? Okay. Did you know you can do that using math in the business world? There's a very simple way. This is a really simplified version of what they do, but how many of you guys have heard of efficiency experts? They go by a lot of names. Efficiency experts move into a company, analyze its processes for a while in corporate culture, and then they try to improve it. Sometimes by firing a lot of people, sometimes by trying to improve morale, sometimes by trying to improve processes, okay? So yeah, if you want to be that person, do it. I'm kidding. Seriously though, efficiency experts make a boatload of money because they're able to find spots like this in processes. Imagine if you could take that function, figure out what things caused that steep spot, that really, really, really high growth rate, and you could make it happen earlier. See, that slope doesn't get to this steepness until this point. What if we could get it to that steepness a little bit earlier in the day or in the process and make it last longer? What would that do to your overall production or efficiency or blah, 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 blah? It would increase it by that much in the same amount of time. Okay, so this is an ultra simplified version of what they do, but they do it very, very well. Do you guys understand why this is so important? Do you see how the math plays into it? Literally where the spot of the second derivative equals 0, that's the most efficient spot. And it's also the point where if you throw good money after bad, we'll talk about what that means in a second, you're not gonna get as much bang for your buck. Yet another phrase. Bang for your buck means here, you're getting a lot of value out of each dollar that you spend in your process because your slope is continuing to grow. For every $1 more you invest, you're gonna get a steeper and steeper growth rate out of it. After this point, that growth rate starts to slow. So you want to identify where that is. Think about this from an advertising perspective. Anybody going into advertising? Marketing? Okay, all right. So think about this from an advertising perspective. What does that point represent? You release an ad, and then what? People get excited about it, right?
People see it, and then it has its lifespan essentially. And
There's the buzz, right? So your sales are growing as a result, and then what?
Like just kind of.
Yeah, at some point, people lose interest. Are you gonna continue to pay the same amount for that advertising after that? No. Your sales will still continue to increase, but you're not getting as much value for your dollars spent on your advertising after this point. So this is the point where you start to think about a new advertising campaign. So you can keep interest.
Could you repeat
This is the point where you start to think about a new advertising campaign, because dollar for dollar, you're not getting the rate of growth out of it that you were
that? So
beforehand.
at the point of diminishing return, you kind of start planning, this is where we got.
This is, at this point, based on our models, this is where we have to start thinking about a new process. Okay? It's a really useful tool. You guys are gonna use it a lot. Okay? So, let's take a look at a real problem. Yeah. I'm so tired. I almost canceled class this morning. Don't cry. I know you wanted to sleep in too, but we're here, and instead of like losing a day, we gain a day. Put it that way. It's a good thing. I just wanted to sleep in so bad. How many of you guys have called in healthy before? Like, you've never called in well? I mean, you lied and said you were sick, but you were really well? Come on, you guys have all done that. Come on. Y'all a bunch of liars.
I've been tempted to.
Bunch of liars.
I think it's
It's a mental health day. Come on. Everyone knows what those are. I just wanted to starfish on my couch and watch Netflix all day. That's what I wanted to do.
Oh, sorry.
I like to drool occasionally. Okay. Probably look at my notes, pick one that's appropriate.
It's a big result of no productivity, but it's productivity for somebody else, not.
Yeah, it's somebody else's productivity. That's exactly right.
That makes.
Okay. All right.
Oh, yeah, I've heard of that, like a custody. Okay.
So we're just barely touching on the idea of concavity today. Let's go back to maximum minima. Okay. You're gonna see a lot of fractions in this section, you guys.
No,
Just
not.
FYI. Yeah, you
I can't see if you remove your eyes.
If you just keep them going.
Can't see if you just.
Don't want to. La 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 la. This is like the math equivalent of being, okay. What's my derivative? 4 comes down and cancels, gives me x to the what?
Third.
Good. 3 comes down and cancels and gives me 2x to the second. Good. 2 comes down and cancels and gives me minus 15x. All right. What can I pull out of all 3 of those things? Good, so we're gonna find maximum, minima. Okay, so I'm gonna set the derivative equal to 0 and take an x out, giving me x squared plus 2x minus 15. Every term that contains an x is a solution, so hang on to this little x. You can't just divide by x and get rid of it, so don't do it. You guys remember my factoring trick? What multiplies to this and adds to this? So we know it's gonna be a 3 and a 5, and it's either gonna be negative 3 and 5 or negative 5 and 3. Which one works?
And then okay.
So does this add to positive 2? How about this one? No, so which one do we take? This guy. The negative 3 and 5. So now we can factor that. 0 equals x times x minus 3 times x plus 5. Okay. So now I set each set equal to 0 and solve. x equals 0, that one's done. X minus 3 equals 0, x is going to equal 3. And then x plus 5 equals 0, x is going to equal negative 5. Okay. How do you determine which one's a max and which one's a min?
Let the positive.
Take a bigger number.
X is equal to 3, so.
Well, you could look at the slopes around them, right? Minima have this slope profile. They have a negative slope before the 0 slope, and then they have a positive after. And maxima have this slope profile, right? Positive slope followed by 0 slope followed by negative slope. So you could either test the values around it, or you could do one other thing. Now that I've given you that tool, what kind of slope does this spot have? Good. So f prime equals 0. What kind of concavity does it have? Positive, negative, 0, what? Is it a happy face or a sad face? Oh, it's a sad face. It's got a negative concavity profile. How about this one? Oops, I can do this. Told you I'm not doing so hot today. I don't know where my brain is. What about the second derivative? What kind of concavity does it have? Positive or negative? Oh, so maxima have a 0 slope and a negative concavity. Maxima have 0 slope and negative concavity. And minima have, what do you guys think? 0 slope and what? And positive concavity. Do you think we could take the second derivative and then test all these points, 0, 3, and negative 5, to see what kind of profiles we get? Could we? Let's try it. So we're going to use the second derivative. To test maximum or minimum. Gesundheit. My response is delayed. You guys have like, oh, we moved on. Okay, what's my second derivative? And you're like, I don't know. Great, what's the derivative of a derivative, guys? You have a derivative, just do it again. What's the derivative? Damn, that was easy. Wasn't so bad, was it? Not super bad. Now, let's test all of those. So let's start with the 0. Y double prime at 0 gives me 3 times 0 squared plus 4 times 0 minus 15 equals what? Negative 15. It's the sign we care about. So when x equals 0, this function is concave down. Is it a max or a min? It's a max. So we have a max at x equals 0. Box that. What's that? Is it good? Whatever it was, is good? Are you, did it like, yeah. Yay! Oh, crack. I love, it's teacher crack. So much fun. Let's do this again. Let's test it 3. So 3 times 3 quantity squared plus 4 times 3 minus 15. This is 27, this is 12. Are we gonna get a positive or negative answer? 27 plus 12 is 39 minus 15 is what? positive something. I would say 14 maybe. All we care about is it's concave up. So we have a min at x equals 3. So much fun. Let's test the next one. Y double prime at -5. That equals 3 times -5 quantity squared plus 4 times -5 minus 15 equals 25 is 75 plus 20 is -20. So what do I have? 25 is 75 minus 20 minus 35 is positive 40. That doesn't feel right. Oh wait, yes it does. It's positive. We have a min at x equals -5. Oh, it's so pretty. Grab your calculators. I would like you to graph the original function. Keep in mind the places that are your maxes and mins. What kind of x min and x max are you gonna need, guys? So everything's centered from -5 to 5 essentially. So we could go from -10 to 10 and be totally safe, right? So far so groovy? So now all you have to do is adjust your y values so that you can see everything clearly. So once again, we're graphing our original function and looking to find those maxima and minima. So much fun. La, la, la. Luga. Okay, so on my first pass, I have x is -10 to 10. -10 to 10. And then I had my y's at -50 to 50. And here's what it came up looking like. So I'm missing just the little bitty tail, right? So I could extend my x min, or sorry, my y min down a little bit, maybe to -100. And I'm gonna see what happens. So if I redraw that, oh my God, it's still not enough, okay. Let's do a window of -150. Then what the hell? Okay, so here's my last window. I finally see everything I need to see. So I'm from -10 to 10, and I'm from -150 to 50. And my final graph looks like this. Do you guys see why I coach you to know where your x values are that matter? Go a little bit further out than that on your min and your max, and then play with your y values so that you can see the whole thing. So how much you want to bet that you know these 3 x values right here, and right here? How much you want to bet? What are they? They're -5, 0, and 3. And are they exactly what we thought? We had a min at -5, there it is. We had a max at 0, there it is. And we had another min at 3. And we used the second derivative to do that. So who's struggling with their calculators? Yeah.
Okay, so first of all, you're doing the entire e to the fourth power. It's not, it's just x to the fourth, it's not in the fourth one. As well, so clear that whole thing out. And break the size here. Close your parentheses on that. Okay, now do x to the fourth. Keep doing it just like that, okay?
Oh, how about -5 or -10 to 10? Look at my mins and maxes. And the reason I do that is I've determined that my 3 points of interest are 0, 3, and -5, so I want to go a little bit out of that. So I go -10 to 10, and that incorporates my -5, my 0, and my 3. Now, what are you going to do to your y values? Try it again. You're backwards. You've got your min is your max, and your max is your min. There you go. Awesome. You'll see it now. And there it is. Good job. Good job. Anybody else struggling with this calculation?
So boring. So Take the light around.
That's what I did. I saw a bad accident on I-20 south.
Like 325?
Yeah.
I-20.
Yeah, with the Subaru, right?
Yeah.
Yeah. I saw
That was terrible.
Yeah, like literally, like this is the car, like the Subaru was like this. Like this is the front of the car and this is the back, right? So if you're going this way, somehow this car ended like this. Oh,
Like,
yeah.
with all the airbag, like,
Yeah, it was super bad. I was like, okay, I gotta slow down.
Anybody else struggling? Okay, Cootie. So what did you learn? What did this teach you guys?
Everything. Shows everything.
It taught you everything.
It all works out in the end.
It all works out. So second derivative allows you to test to see whether your points of interest, what we call them, are critical values. To see whether your critical values are maxima or minima. An easy way to check this is to graph it and see that, yeah, what we did with the second derivative here shows exactly what we expected. Maxima and minima are exactly where we needed them to be. How do you guys feel about that?
Why did you increase it to -115?
How did I do that?
No, why did you?
Why? Because I wanted to see the very bottom. I wanted to see the whole function. You see how it crawls off my screen right here? I wanted to see the whole thing. So
You increased your Y.
I dropped my y minimum. Just imagine pulling this down so that I can expose this, okay? So that's all I did. So that's why I draw these this way, so that you can see exactly where my maximum minima are on my x and y. Okay. You guys wanna look at another? Just one more?
One more.
One more.
Let me take a picture.
Yeah. Okay. All right. The the y, not y-intercept, but the y values corresponding. So let's say you get x's that are like here, here, and here, and you get the corresponding y is up here, the corresponding y is down here, and the corresponding y is right here. Which one of them's which one of them's do you think is a maximum and which one of them's is a minimum? I'm just gonna go with it. The hell with it. What do you think, guys? Just for giggles. At a guess.
Top one is the maximum,
Probably, yeah.
and the bottom is the minimum,
Probably, yeah.
and then the other one is
Something
kind
like
of-
that.
Yeah.
Yeah, probably. So the only way to know for sure is to do that second derivative test, which honestly is faster because you're working with an easier derivative, right? The derivative is always simpler than the original function in a lot of ways, especially in this chapter. The derivative is always going to be simpler than the original function. So let's go ahead and take our first and second derivatives just for giggles. What's my first?
3x squared minus 3.
Yeah, minus 3. And what's my second derivative?
6x.
Yeah, 6x. Okay, that's not so bad. You okay? I just heard it like, okay, make sure you're all right. So now, we're gonna find places where slope is 0. Find where slope is 0. So 0 equals 3x minus 3. 3x squared, rather. What do we do?
Plus 3.
Yeah, move the 3 over,
Divide by 3.
and then do what?
Divide by 3.
Divide by 3. So now we have 1 equals x squared. What do I do now? Square root both sides. So I'm going to get x equals plus or minus 1. Right? Because negative 1 times negative 1 is 1. So the square root of 1 is also negative 1. Right? Okay. So I have 2 x values. So I have x equals 1. And I have x equals negative 1. Now we have to identify which is a max and which is a min. It gets a little ticky-tackier later because there's something called a point of inflection, like that, where it's neither a max nor a min. But when we get deeper into concavity, you'll see what I'm talking about. But for now, we're just talking about maximum and minimum. Groovy? So, how do we test it? Yeah, we're gonna test it in the second derivative. So, test for maximum and minimum. And as a reminder, a max has what kind of concavity? Up or down? Negative, right? Maxima have a sad face. What about a minimum? Happy face. Oh. Okay, groovy. So let's test negative 1 first. Y prime, double prime of negative 1 is 6 times negative 1. What's my sign of my answer?
Negative.
That's a sad face. So x equals negative 1 is a max or a min? I heard it. You guys are way overthinking this. I heard it. Max, thank you. It's a maximum. And what about y double prime of 1? Equals 6 times 1 equals positive 6. That's a sign of positive. It's a happy face. Is that a max or a min? It's a min. So x equals 1 is a min. Grab your calculators, guys. We're going to graph it to verify. What are we graphing? The original, the derivative, the second derivative, what? The original. Yeah. This guy up here. So pretty. Remember, you may have to change your X's mins and maxes and your Y mins and maxes. So X cubed. Yeah, you're definitely gonna have to change this. So on your original window, you get something that looks like it's flattened out in the middle and then shoots back up again, right? But we know we have maxima and minima in there, so what are we gonna do to our Y values? Yeah, we wanna make them smaller because we wanna see that detail. Imagine grabbing that spot and blowing it up, right? So we're gonna make our maxima and minima a little bit smaller on our Y values. So I'm gonna go from negative 150 to like say 25, and from 50 to say 25. Oh, yeah, you can. Negative 25 and 25. Oh, look how pretty. Aw. So here's my little graph now. And I went from 25, negative 25, negative 10, 10. Or you can just go zoom standard and they'll get you there. My looks like that. So here's negative 1, and here's positive 1, as promised. Questions? Yeah?
So when you're taking the derivative, it's only approximate, not really exact.
Clarify.
Just because when I did second trace, I looked up the max and min, and it doesn't give me exactly 1 or negative 1.
It should. You did second trace, not just trace?
Yeah, second trace.
I think it's because of the, F of X plus H minus F of X. So, yeah, it's essentially one. Mathematically,
Bad idea.
that's right. That's
I was struggling
why.
too.
Wasn't as much as-
We're home on the struggle bus today.
But it should
How do you guys feel about this?
Coming of like
So it's not really touching negative 1, it's like a little away, is that?
It's not about touching negative 1, it's about having a function at negative 1. Remember, it doesn't have to touch the x-axis at that point.
Okay, I see.
It maxes out at that x value. And it mins out at this x value, approximately. I mean, yes, but my sketch is imperfect. All right, here's your homework for this. I'm not gonna give you any homework at a 9.8, because that's basically how to take a second derivative. Oh my dear God, you guys already know how to do it. You just didn't know you did. So 10.1. Oh yeah, I have a handout for you guys. Let me give that to you first.
Literally, so grateful.
I'm gonna pass them this way instead.
My house. I'm on 9.5. So I'm gonna do all of this. Yeah, so I'll figure out what to do.
So today, obviously, I just asked her like if she could go over her two chapters because I feel like, well, I don't know why you guys keep struggling. We're gonna go over like the whole
Well, I think I
car
might.
crash.
Can you go to your office hours tomorrow? You'll have that.
I work, or I run my dog.
So in this handout, which is one of my crappy old ones, you can see the
Every day you
difference
go?
hopefully between my crappy
Oh,
old
really?
handouts and my good
Okay,
new ones
then I
that I've
can go
rewritten for
tomorrow.
clarity. This one's a little sketchier.
Yeah,
I apologize for the pun.
Oh, here you go. Oh,
It's okay.
we have double over here.
Oh, we do?
It's okay.
Yeah.
Do. Yeah, okay. Good times. Here's your homework.
Yeah, but
On 10.1, I'd like you guys to please do 11, 13. Ads and sales. And productivity. I can't spell today. And that's good. Keep it simple today. Because I know you guys aren't gonna do it anyway, you're gonna spend your weekend studying for the exam. So when I see you Thursday, come with questions for exam 1. Once again, you guys should have the review checklist. If you don't have a handout or you're missing something, come talk to me. I have extras of almost everything up here, except for 9.1. For some reason, I'm missing those. Just didn't have enough of them.